Okay, Bismillah ar-Rahman ar-Rahim. This is Dr. Ali Muqaibel, and today's lecture is about orbital mechanics of satellite communications. When we deal with orbital mechanics, we will be covering orbital mechanics as a first part. We'll look at angle determination, orbital perturbation, and then we'll go into orbital effects on the communication system performance. So let's start with the orbital mechanics. The topic we'd like to cover are listed here. We'll look at developing the equation of the orbit, the kinematic and Newton's law. We'll look at circular orbit and velocity and period. We'll look at solar versus sidereal day, reference coordinate axis, Kepler's three laws, review of ellipse analysis, and then we'll look at conditions for geostationarity, locating the satellite in orbit, and we'll conclude with the orbital elements. We will be having some examples. So let's start by developing the equations of the orbit. How is the orbit achieved? How do we put satellite in orbit? What are the laws that describe the motion of an object orbiting another body? Satellite, first, you need that we have the Earth, and satellite must be beyond the bulk of the Earth atmosphere. So it won't be very close. And most of the satellites are placed 400 kilometers above the Earth. Even at that height, we will still have some atmospheric drag. That we're not in total free space. There will be some friction. We'll have some atmospheric drag. For example, and these numbers are just to give you an idea, a satellite injected at height 397 kilometers in the 9th of June 1999 had decayed to 360 kilometers. That's about 37 kilometers by the end of 1999. That's in few months. And the satellite must have fuel to maneuver to correct their position. And of course, this is usually time limited, which means the fuel that comes with the satellite at the launching time. So it could last for 15 years or so, depending on how much atmospheric drag are there, how much correction is needed. We cannot rely on solar cells to maneuver a satellite with high weight. So we need to understand the fundamental Newton laws that describes the motion of a body, coordinate axis, so that we locate things according to different coordinate axes, so to determine the orbit and the various forces on the satellite. Okay, so let's start. The kinematic equations and the Newton's law. Here is the Earth, and here is a satellite. Satellite will be moving a distance. This distance is referred to as s by a given time t. So we have small t to represent the time, s representing the distance, and then we have the initial velocity at time equal to 0. So we'll refer to it as u. You could use v naught. We're using u here, just to follow the notation of the book. The velocity at a given time is v, and the acceleration is a. F is the force on the object. So we know from Newton's second law that F equal to ma. The force on the satellite equal to the mass multiplied by the acceleration. That's Newton's second law. We know this from before. Those are the kinematic equations, laws that relates velocity with speed and acceleration. Remember that v, the velocity at a given time, equal to the initial one plus the acceleration times time. So this is kind of logical. We can think of the distance covered as the velocity times time. That is, if the object is not accelerating, we have distance equal to velocity times time. And if it's accelerating, then we need to multiply the acceleration by, or the velocity by the time. So the velocity, we can take the average velocity between the initial and the final. So we have 1/2 times at times t. So this relates distance with velocity. And also we can relate the initial velocity with the final velocity using v squared equal to mu squared plus 2a times s. Okay, remember that we measure force in Newton and Newton is equal to mass times A. So we can say that the Newton unit is nothing but kilograms times mass times meters per second squared. All right. So how do we get the acceleration? We know that from physics that objects attract each other. So if we have two big masses, then we expect there is two planets where there will be some acceleration between them, some gravitational force, and force will cause acceleration. So in general, we can say that the acceleration equal to mu divided by r squared. So it depends inversely on the distance. So it's mu divided by r squared. Now what's mu? Mu equal to g. Mu is the Kepler constant. It's 3.9861352 times 10 to the power 5 kilometers cubed per second square. It's the universal gravity constant multiplied by the mass of the Earth. So if you want to do the multiplication, it's going to be g here, which can be written in two different notations. Remember here that we have we're using the Newton and kilograms, meters. So this is just the same number, but with adjusted units, because we have the cube. We have here kilometers or meters. So that gives you the square. Now, if you look at the mass of the Earth, it's given by the following note. I'm not expecting you to remember these numbers, but I'd like you to understand that in general, acceleration due to gravity is given by the following. And if it's the Earth, we have g times me, which is given by the following. I am using the colors here so that you can follow up. G is the universal gravitational constant, and U is the Kepler constant. Me is nothing but the mass of the Earth. Okay, so now for stable circular orbit, if you want to have a circular orbit, then we need to look at the diagram of the object, the satellite. And we know that there are two forces at minimum are acting on the satellite. One is the centripetal force, and the other one is the centrifugal force. And here is the direction of motion. We need to relate this to the parameters of the satellite. So the attraction force, just we had the equation before, it's equal to mu divided by r squared. But mu equal to gm. That will give you the acceleration. And know that from Newton's second law, force equal to acceleration times mass. And of course, we have the centrifugal force, which equal to mv squared divided by r. In fact, this is just kind of making things simple, but what happens is that the object is moving in a direction and it's in a continuous falling. Okay, now forces on a satellite, we just mentioned that there is an inward force and there is an external force that acts on the satellite. And often when we look at the radius, I'd like you to know that the radius is nothing but a sum of two quantities. It's the height from the Earth plus the radius of the Earth. So the radius of the Earth is nothing, or the altitude of the satellite, which is the radius of the Earth is 6738.137 kilometers. That's the average radius of the Earth. Okay, of course, Earth is not exactly a sphere, and there are mountains and valleys and what have you, but this is the average value. So we have the inward force. Now notice that we have a minus sign here. Once you start using vector notation, which means there is a direction. So we're using r naught is the directional vector in the direction of going out from the center of the Earth to the satellite. And this way we have a minus sign. So we need these forces to be equal. So this is the inward force. It should equal to the centrifugal force, which is going out. Okay, so now if we equate the two together, we'll get mv squared over r times gme times m divided by r squared. We can see that I'm going to just use subscript to distinguish m in general from the satellite. So we have r sub s and we have m sub s. The mass of the satellite cancels out, so it's not the exact mass of the object that determines the distance and velocity. It's because it cancels out. So now we can solve for the, of course, with r squared, the square will cancel with r from here, and we get the velocity by taking the square root of both sides. And this is what remains. We can also solve for r if we are interested in the radius. So it becomes r equal to gme. So I think it's time to collect some equations. Those are two fundamental equations. The velocity, sorry, and the radius of, if you know the velocity, we can use the velocity to find the radius and vice versa. Now we can represent the period, how much time it takes for the satellite to rotate. And for that, we know that the total distance, to find the time, it's distance divided by speed. So the distance is, it's this arc, it's the circumference of a circle, which equals to 2 pi times rs. So that's the distance, divide by the speed, and I got v from here. If you divide, I got the following expression. So either you find velocity first and then you divide, or we can just substitute the expression and we got the following. So since the satellite is in an orbital, in a circular orbit around the Earth, then it is going to cover, so it's going to cover the circumference, which is 2 pi rs, in the following period. So we have three equations now: velocity, radius, and period. Okay, here is an example. It says NASA Hubble Space Telescope is placed at a circular orbit, in a circular orbit around the Earth at altitude or height above the Earth's surface of 595 kilometers. Determine the speed of the satellite in orbit and the satellite orbital period. So we can see that what we are giving is altitude, so we need to add that to the Earth average Earth radius. So rs will be the sum of these two. And also we know the Kepler constant, so we can say that the velocity, going back to the equation, and we substitute, that will give us 7.5606 kilometers per second. That's not per minute, it's not per hour, it's per second, and that tells you how fast the satellite moves. In satellite calculation, we usually avoid oversimplification, because these are going to matter. We have to be as exact as we can. This is rocket science, in fact. So if you want to find the period, then it will be directly 2 pi rs divided by the velocity, and if you substitute, we got 5,794.83 seconds. You can convert that into hours, minutes, and seconds. You can divide by how many seconds are in 1 hour. So 60 times 60, which is 3600. If you divide 3000, you get 1, and you keep the remainder, and you keep continuing to find the number of minutes and seconds. So this satellite, this space telescope, circled the Earth in 1.6 hours. It's 1 hour, 36 minutes, 34.83 fraction of a second. That's how fast the telescope is moving. Of course, when it comes to communication, that would have an impact on how to communicate with a fast object, Doppler effect, and what have you. Now, before we continue, there is an important concept that we need to understand before we go into geostationary satellites. This concept is the concept of a sidereal day versus a solar day. A sidereal day is the time between consecutive crossings of particular longitude on the Earth by any satellite other than the Sun. And we'll see why we exclude the Sun. While the solar day is the time between consecutive crossings of any particular longitude of the Earth by the Sun, Earth axis. So a solar day is exactly 24 hours. That's the thing that we know. But there is this sidereal day, which is a bit less than 24 hours by 4 minutes. In fact, 3 minutes and 56 seconds approximately. Why is this difference? I'll explain it in a figure in the following slide, but just let's state it and then we go to it. By the time the Earth completes a full rotation with respect to an external point, not the Sun, it has already moved its center position with respect to the Sun. The extra time it takes to cross the Sun-Earth axis average over 4 full years. And that will give you that's why in every 4 years we have 366 days, which is 3.93 minutes per day. That's the approximation we had. 3.9, sorry, maybe I misstated. It's 3.93 minutes per day. So the remaining here is 3.93. Okay, we'll see this on the diagram and we'll try to explain it. Okay, so this is a solar day. Where if we do a little bit of, before we go into the calculations, you can see that the sun is here and the earth is rotating. If the sun was fixed, then it will finish in 23 hours, 96. It will finish in less than 1 day. But because the sun is moving, or the earth center is moving relative to the sun, so we need to rotate. If we're still, we'll finish in a sidereal day. But this extra angle we need to rotate is what makes the normal day, because we measure things relative to the sun, but our position have already changed relative to the sun by 0.986 degrees. So now we have to complete that extra time. Okay, so the fact that we know that the earth takes 24 hours, 0 minutes and 0 seconds to make one complete revolution is not correct, because this revolution, if measured relative to the sun, is going to be 24, but relative to itself it will be less than that. So let's do a bit of calculation. In 4 years we have 1461 solar days. We added this 1 day for this difference, and in 4 years the earth moves 1440 degrees. That's 4 times 360 around the sun. In 1 solar day the earth moves 0.98 degrees. So in fact, if you divide the total number of solar days by the number of degrees around the sun, you will find that in every solar day we move 360.98 degrees, and in 1 sidereal day the earth moves 360 degrees around itself, while in 1 solar day, which is 1440 minutes, the earth would have rotated more than that, which is an extra degrees because of the sun changing its location. So difference is 3.93 minutes. I hope the basic concept is clear. It's just if we were stand still, we would have finished the rotation, but because we have difference in relative position, so relative to the sun, we have 0.986 extra degrees. So now we're ready to go into second example. I leave this example for you. So just state the example. Please share your answer. The radius of the geostationary, this geosynchronous or geostationary satellite orbit. We need to find the radius. What's the radius that will guarantee geostationarity? The speed of the satellite in a geostationary orbit. So once we find the radius, remember the equation we had, but we have velocity, time, and radius. What is given to us here? We are told it's geostationary. So this is why we introduce the solar day and the sidereal day. So we need to use the sidereal day length to calculate the orbit radius of the geostationary satellite. So we can say that the period is 86140.09 seconds. That's the time for one complete sidereal day. The radius of the geostationary Earth orbit is calculated by substituting into the equation. I know the t, I will solve for r, and I got 42164 kilometers. Therefore, the altitude, if you want to find the altitude, you subtract the average Earth of the Earth, and that will be 3578 that's 3570 kilometers. That's the average. We know this number before, we have seen this number before. So the speed of the geostationary or the geosynchronous in orbit satellite is given by just another substitution. We have found now that how much r is, and we got 3.0747 kilometers per second. That's per second once more. Okay, so this example is good because it deals with geostationary satellite. In the following table, we share the orbital velocities and period. So given the first column of height, okay, write a MATLAB code to generate other two columns. Where is the trick? And I can share this with you in my website, in the website for the course. You can have the MATLAB code, or you can just, from the PDF file for the slides, you can just copy and paste this maybe with minor adjustment. So this what we are doing here is basically we are defining a program that will generate, given the height, will generate the orbital velocity and orbital period. So clear all, close all. We have the constant here, Kepler's constant, given. We have the mean Earth. Remember that the E equal to 10, its multiplication by 10 raised to the power 5. I am defining the mean Earth radius of the Earth in kilometers. Make sure that you get the units right, because this is the main mistake that we expect. We get the orbital height. I'm starting with a very low number to assume that the object is on the Earth. So instead of saying 0 and create some mathematical issues, we're saying 1 times 10 raised to the power minus 19. Then we have these values, 3, 35, 10, 1, 46. You can see these numbers. These are the orbits. So I will do them at once. The first step is to define the radius to be the sum of the altitude with the Earth. So we have r here. Then we find the velocity by just direct substitution in the equation. We find the equation for the period. And of course, once we get the number, we divide by 60 to find and get the floor to get the number of hours. And then take the remainder, t minus th, times 60, which we remove the number of seconds. What remains, we divide by 60. We take the floor, we get the minutes. And then we removed the minutes and the second and the minutes, the hours and the minutes, and what remains is the second. And this is how we got these numbers. Okay, so please stop now and just execute this MATLAB code. Make sure you do it yourself, because this is the way to learn. If you have any question, please leave it in the comment section.